And these warm-up questions are different in the sense that we don't really have like the binomial terms, right? The factoring. There's not a whole lot of factoring involved here. But all these terms are rational, right? Rational just implying the fraction part. Um, and reducing down the numbers is the one thing that we need to work on. And next year in pre-calc, you're going to be expected to do this from day one, okay? And from here on out, I'm expecting every expression you work with to be completely simplified. So what does that mean? Like when we see 21/15ths, why is that not simplified? Well, that needs to be reduced down. So what some of you know about reducing down is what you're going to do is look for a number that divides the numerator and denominator and divide it by that same number. 21 and 15 are both divisible by 3. And it has to be by the same number. And when I divide both the numerator and denominator by 3, I get that this reduces down to 7/5. So 21/15 is the exact same value as 7/5. Now, really what's happening, okay, and I've actually shown that to us in our calculators, right? I've talked about if you take any fraction and do the division in your calculator, it'll give it to you as a decimal, but then all your calculators can take that decimal and convert it to a fraction. What's really happening, your calculator is saying, I see 21, but instead of it thinking about it as 21, it factors 21. And it says 21 is equal to 7 times 3. It does the same thing with 15. It recognizes that 15 is equal to 5 times 3. And then by factoring it, it recognizes that there's that common factor of a 3 in the numerator and denominator, and they divide out because 3 divided by 3 is 1. And that's how we get to that 7/5. Okay, so you don't need to factor it out, but that's really what's happening, okay, when we reduce it down. Okay, we are essentially factoring. We're just skipping writing that part down. So with numbers, you will always look for what divides both the numerator and denominator. We want the largest number that divides them both. Okay, number 2, this actually gets out an exponent rule. We will have an entire couple days where we work with exponent rules. For now, when I see this, I just write out what x to the 7th and x to the 5th means. That's basically me factoring it. Instead of x to the 7th, that's x times x times x 7 times. So 4, 5, 6, 7 x's. And then I do the same thing with x to the 5th. 1, 2, 3, 4, 5. And then just like before, now that everything's factored, anything that's the same in the numerator and denominator divide out because x divided by x is 1. So I'm going to get 3, 4, 5 x's to divide out, leaving me with just an x times x in my numerator, and x times x is x squared. The denominator is really 1, okay, since all those x's divide out, it equals 1. But you could write that as x squared or x squared over 1. Now, instead of me writing that out all the time, like if you saw this on a homework assignment, what's an easier way that I could work with these terms to get x squared? What operation can I do with their exponents? How do I go from 7 and 5 and get to 2? Subtract them. Okay, so it's the top exponent minus the bottom. Right? So applying that same idea to number 3 here, if I take 5 minus 7, that's negative 2. So this ends up equaling x to the negative 2. Now, there's another way that we can write that x to the power of negative 2. And if you think about this same idea, well, I've got 5 x's in my numerator, 7 in the denominator. So I get all 5 to eliminate in the numerator. And I am left over with 2 x's in the denominator, which is equal to 1 over x squared. Okay, so that gets out a different exponent rule that when we have negative exponents, that changes where that base is located. Okay, it goes from being in the numerator with a negative exponent, and it moves it to the denominator and now with a positive exponent. Okay, so really when I see x to the 5th, x to the 7th, I still think about it this way. I go, oh, I can cancel out 5 x's in the numerator. I can cancel out 5 in the denominator, leaving me with x squared in the denominator. And because there's nothing left in the numerator, it's just a 1. All right, questions there? All right, now to number 4. All I did with number 4 is I combined 1 and 3, or excuse me, 1 and 2. Because a lot of students, when they see 4, they feel like that 21 and x to the 7th, they're stuck together. But that's not true. This is really 21 times x to the 7th divided by 15 times x to the 5th. Okay, so basically we just treat it as 2 different problems. Reduce down to 21 fifteenths. That would be 7 fifths. X to the 7th divided by x to the 5th is just x squared. And that's an x squared in the denominator, or excuse me, in the numerator. So you could actually write this in 2 different ways. You could write it as 7 times x squared divided by 5. That is the same thing as 7 fifths times x squared. Okay, so know that these are the same. All right, and that's kind of like the first problem on your homework assignment, actually. It's very similar to this, where you have, that's called a monomial, so it's just one term with a coefficient. And those coefficients get reduced down separately. Okay, the last 3, they get at kind of what our solutions look like when we carry out the quadratic formula, right? Where we get this 2-termed expression in our numerator all divided by a single value in our denominator. So there's a couple ways of how we can simplify this. The easiest way, and what I would encourage us all to do, is when we have multiple terms all getting divided by 11, write it out where each term is getting divided by 11 separately. Because then I can do the division and simplify each term individually. 33 divided by 11, that's 3. These terms, I have a 44, a root 5, and an 11. I can only reduce down numbers that are like terms, meaning I can reduce down numbers with numbers. I can't reduce down square rooted numbers with whole numbers. Okay, so this root 5 does not get reduced down at all. What is going to get reduced down is the 44 divided by 11, which equals 4. So that's minus 4 root 5. Another way that we can do this is if you identify that your numerator has 2 terms and they're all getting divided by 11, it's really just us dividing all of those terms by a common factor. So 33, 44, and 11, those are all divisible by 11. And then that gets us to this term by dividing everything by 11. Okay. Now that changes a little bit with number 6. Because if we treat it how I suggest, where we do the division separately, I get 33 divided by 22 minus 44 root 5 divided by 22. And so 33 divided by 22, that gets reduced down by me dividing both by 11, and that becomes 3/2. Okay, but then 44 divided by 22, that's a whole number, right? That ends up being 2. Okay, I can divide both of those terms by 22. So that makes that minus 2 root 5. Now, a lot of times, how you're going to see this answer simplified, like this is absolutely okay how I have it written. You're going to see this expression simplified where they look at 33, 44, and 22 and divide out the common factor of all 3 of those terms in one step, all of which are divisible by 11. And that changes the simplified expression slightly, where it becomes 33 divided by 11 is 3. That's the same 3 I have right here. 44 divided by 11, that's 4. And the root 5 does not get divided. And 22 divided by 11 is 2. So this expression factors to either term here. Okay, these are both the same thing. And if you take this answer that I just came up with, well, 3 divided by 2 gives me that 3 halves. And if I take 4 root 5 divided by 2, that's how I get it to be 2 root 5. Both are perfectly acceptable, and both are considered to be completely simplified. I think this is kind of your best method to go to, though. All right, so let's do that same idea for number 7. Let's just think about what can we divide 21, 36, and 9 all by. And they're all divisible by 3. And so this expression is 7 plus 12i root 7 divided by 3, which could also be simplified if you do it individually to 7/3 plus 4i root 7. Okay, so there are kind of, I'd say there's a few different tricks, right, with simplifying these rational expressions. And it takes practice. So that's why, again, tomorrow I'm perfectly okay with us spending the time to work through these and struggle through them. Okay, because again, this is going to show up for every math class you take from here on out. Every term will need to get simplified. Okay, before we move on and finish the notes from last class, are there any questions with any of these warm-up expressions? Okay, then I'm going to have you all get the notes out from last time. Remember, you have a dividing or a 6.1, 6.2 simplifying rational expressions packet. If you need a copy of this, I'll come around and give that to you right now. Okay, so a lot of the same ideas that we worked on with the multiplying, the dividing, and just the simplifying any expression that's rational that we talked about on Friday is still going to apply with the adding and subtracting. We still have domain restrictions. We still can't divide by 0. So we have to consider to rule that out. To exclude any values that make us divide by 0. A good place to start when we are adding, subtracting, or doing any operation with rational expressions is to factor everything completely. So let's start right there. 5x plus 1 does not factor at all. X squared minus 9. I recognize that a is 1 there. I don't see a b term. B is going to be 0. Okay, so this is x squared plus 0x minus 9. And thus that factors to x plus 3 and x minus 3. Then I have minus. 4x minus 2 has a greatest common factor of 2, making that 2x minus 1. And then the denominator stays the same of x plus 3x minus 3. Okay, so when we're adding or subtracting fractions, and we did this with the warm-up on Friday, where we just did it with numbers. And you all told me that with numbers, we need the denominators to be the same. When they're the same, we can combine the numerators just like we normally would when adding or subtracting. Well, in this case, the denominators are already the same. So these fractions or these expressions are ready to be added. So I'm going to take the 5x plus 1 and the negative sign and the 2 times 2x minus 1. That's going to be my new numerator. This is always a good idea to do. Okay, to circle the numerators and the sign. And then just copy that down. Don't do anything else with it. That's 5x plus 1 minus 2 times 2x minus 1. And it's all getting divided by that common denominator of x plus 3x minus 3. And now the numerator, we can simplify that. Okay, I can simplify it by distributing this negative 2. That makes this negative 4x plus 1. And the denominator stays the same. X plus 3x minus 3. The numerator can still simplify further where I can combine like terms. So 5x and negative 4x, that's 1x. 1 plus 1 is 2. Oh, that shouldn't be 2. That should be positive 2 right here, right? Negative 2, negative 1, that's positive 2. And then 1 plus 2 ends up being 3. So this is really x plus 3 divided by x plus 3, x minus 3. And then this x plus 3 is simplified. So that's technically a factor in that numerator. And it's the only factor. And because I have x plus 3 in both the numerator and denominator, they divide out, giving us our simplified expression to be 1 divided by x minus 3. With the domain restrictions that all stem from where we started, where the denominator was x squared minus 9. And from x squared minus 9, we rule out that x cannot equal 3 and x cannot equal negative 3. It has those domain restrictions. So what ends up happening here a lot of times, students will see this and they're like, oh yeah, those x minus 3's divide out. And then they'll say that the final expression is just x minus 3. That x minus 3 is in the denominator though. I can't just magically move it to the numerator. Okay, so that's where a lot of you will recognize that these divide out, but you're like, wait, what should the numerator be? And this is why I always emphasize that these terms divide out because they equal 1. Right? No matter what I plug in for x here, I'm going to get some number divided by itself, always giving me 1. So that's why this ends up being 1 divided by x minus 3. All right. Any questions there? Before we step it up a notch. Okay. We'll go and flip the page. And now we're going to actually need to work on getting a common denominator. All right, and again, a good place to start is to factor everything. So numerator, x plus 2, that's factored. 2x minus 3, that's factored as well. 4, that's factored. There's nothing I can really do with that. And x plus 3, that's factored. So everything's factored here. Now, I'm recognizing my denominators are not the same. So that's where we're going to have to start. How can we accomplish getting that common denominator? And I'm going to actually just rewrite this problem just so I have a little bit more space. And I also think it's helpful once we decide everything is factored to put parentheses around each individual factor. Now, just like what we did with numbers, what can always work is if you take this first expression and you multiply it by the denominator in the other expression, you will get a common denominator. Okay, so I'm going to multiply this whole expression by x plus 3 and divided by x plus 3 because this whole part is 1, right? So by me multiplying that expression by 1, I'm not changing the value of it. You're not changing what that value or what that expression is. But by giving that x plus 3, I'm working towards getting the denominators to be the same. And then I can add and subtract after that. So right now, my denominator is x plus 3 and 2x minus 3. This second expression has the x plus 3, but it's missing this 2x minus 3. So I'm going to multiply it by 2x minus 3. And from here, I'm going to multiply the fractions, which that's what we did on Friday. Remember, there's really nothing to do with the multiplying, right? It's just numerators times numerators, denominators times denominators. So you could just extend this division bar if you wanted. I'm going to actually write it out this time. And over the denominator, x plus 3, 2x minus 3. Okay, so that's just me multiplying after finding, multiplying by each expression by 1 to get the common denominator. Again, I don't think we need to write that step out because I talked about on Friday that when we're multiplying fractions, the numerators get multiplied by numerators and denominators by denominators. So you can, in theory, just extend that division bar and you've multiplied them. All right, so now I recognize the denominators are the same. So I'm going to add or subtract the numerators just like I normally would. And I always start that out by just circling all the numerators and the sign in between the expressions. And I'm going to just copy that down as my new numerator. So the new numerator is x plus 3 times x plus 2 minus 4 times 2x minus 3, all over the common denominator of x plus 3, 2x minus 3. And now the numerator needs simplified. Okay, so we've at least been able to add the fractions. Now our task is to simplify the single expression we have. This x plus 3 and x plus 2, they're going to get FOILed. So I'm going to do x times x. That gives me x squared. X times 2, that's 2x. 3 times x is 3x. And then 3 times 2 is 6. From the second expression, we have this minus 4 times 2x minus 3. I would highly recommend distributing this 4 as a negative. In fact, anytime you're subtracting expressions, distributing that negative makes the rest of the work so much easier because now I'm just combining like terms. I don't need to think about the subtraction. So anytime we are seeing subtracting, just distribute the negative. So this is negative 8x and then plus 12. All over the common denominator of x plus 3 times 2x minus 3. Well, that numerator has a bunch of like terms. There's only 1x squared, but I have 2x and 3x is 5x. 5x minus 8x is negative 3x. And then 6 and 12 is 18. All over the common denominator. And so up to this point, we've added the fractions, or I guess in this case, subtracted the fractions. We've simplified the numerator to a point. We now need to check, does this factor? If it factors, we might have more simplifying to do. Okay, so I'm asking myself, are there numbers that add to 18, or excuse me, add to negative 3 and multiply to 18? My head goes to, oh yeah, 6 and negative 3. But if I take 6 and negative 3, are they going to multiply to a positive 18 now? Nope. So they actually do not factor, which is good for us because that means we're done. Okay, the numerator does not factor any further, and thus there won't be anything else that divides out. So does it factor? No. Only thing we need to add into this is our domain restrictions, and that x cannot equal negative 3. And then from 2x minus 3, we would rule out 3 halves. All right. The timing of this is working out really well. Number 8, I want you to do your very best with it. It is a little bit more complicated than I just did. At the very least, factor everything. Try to get your common denominator and see if you can simplify from there. Do your very best with it. All I need you to do is try. It does not need to be right. We will go over it before we leave here today. I'll give you like 5 minutes. So starting with the factoring of both denominators, x squared plus x minus 2 factors to x plus 2 times x minus 1. X squared minus 1 factors to x plus 1 times x minus 1. So in this case, it's always a good idea to start with what do both denominators already have in common? They both already have an x minus 1. So instead of over multiplying and adding in more terms here, because a lot of students, they might be like, oh yeah, I'm going to take this entire denominator, multiply this fraction by x plus 1, x minus 1, and the other fraction by x plus 2, x minus 1. You get a huge mess that ends up having to simplify later. So I'm like, they already have x minus 1s. This first fraction, though, is missing the x plus 1. So I'm only going to multiply it by x plus 1. The second fraction is missing the x plus 2. So I'm just going to multiply it by x plus 2. So this is us getting what's called the lowest common multiple for all these denominators. Okay, if you add in more terms, there's just way more simplifying that has to happen down the road. So that makes my denominator x plus 1, x plus 2, x minus 1. So this is me just doing the multiplying after finding the common denominator. Then I'm adding the numerators while I'm also working on simplifying them. So the x squared comes from x times x. 3x comes from x times 3. 1x from x times 1. And 3 times 1 gives me 3. Then this is a positive 2 distributing to the x plus 2, making that 2x plus 4. All over that common denominator. And then combining like terms gives me x squared plus 6x plus 7. I would then ask myself, does this factor? If it does, I might have more simplifying that has to happen. Luckily, in this case, it does not factor. There are not two numbers that add to 6 and multiply to 7. So that expression is simplified. And then we rule out all the numbers that make us divide by 0, which are -1, -2, and +1. Okay, that is it for today.